The next speaker is Jack McKoen from the University of Alberta, who's going to tell us about toward functor quasi-categories in Lean.
Thank you. So hi, everyone. I'm going to talk about quasi-categories. So I'm interested in infinity category theory and formalizing infinity categories. And so I've been putting them together in my own little project. So if you saw Emily's talk on Tuesday, I think, where she went over the Infinity Cosmos project, that's sort of a very broad project that intends to cover a lot of stuff. Mine is very hyper-specific about one very specific result involving quasi-categories. So first I'm going to sort of talk about quasi-categories and what I want to show about them. Then I'm going to go into the structure of the sort of proof that I'm going to go through. And then I'm going to explain sort of what has been done so far in Lean and what is left to do, and where I'm going to go next. So a quasi-category is a pretty useful model for infinity categories, which is not really obvious from the definition. So it's a simplicial set, which is a certain type of functor, which satisfies what's called the inner horn filling condition, which means that every morphism from an inner horn factors through the inclusion of that horn into standard simplex. And it's, for my talk, I don't think it's very important that you really know what, if you're not familiar with like simplicial sets, I don't think it's really important that you know what the horn is or what the standard simplex is. It's just important to know that they're like distinguished simplicial sets. So this is the definition of quasi-category as it appears in MathLib. It's been there for I think about a year now, but no one has done much with quasi-categories yet. So what we have in MathLib is we have a lot of simplicial set API, especially recently, thanks to the Infinity Cosmos project. And me, I've done a bit of simplicial set API. We have the definition of a quasi-category, and we have that the nerve of a one category is a quasi-category, but we don't have much else. I mean, in terms of results explicitly about quasi-categories. So one way to sort of to help build up infinity category theory in MathLib is, I mean, there's the Infinity Cosmos project, which does it in sort of a far-reaching, benevolent way. But for me, I just chose a goal somewhat arbitrarily and decided to build up exactly what I needed to get there. So it's very, very specific. And so this is what my goal is really. So we have the internal HOM of simplicial sets, also called the function complex, or when X and S are quasi-categories, we might call it the functor quasi-category. And I don't think it's really too important how it's defined, but it's very importantly, it's the function complex is right adjoint to tensoring, which is a really nice property. And so in Lean, in MathLib, it's defined sort of in a way that's maybe not easy to reconcile with what I've written down, but it's written down more generally in MathLib, but it's the same thing. And so we want to show that the function complex of X and S is a quasi-category when S is, and then we can call it the functor quasi-category because then we know it's a quasi-category. So that's what I want to do. And the idea of the proof is that the quasi-category condition on the function complex is a type of lifting problem, which we can do some gymnastics to reduce to the quasi-category condition on S. And so what we do is we're going to introduce a sort of lifting calculus, just a way to better deal with lifting problems, which brings me to sort of the structure of how we're going to prove this. So to introduce lifting problems, we say that a morphism F has the left lifting property against a morphism G, and vice versa. If every square of the following form, every lifting problem admits a lift, which is that dotted arrow in the middle, which makes the two triangles commute. And as shorthand, if we have a collection of morphisms T, LLP of T denotes the collection of morphisms which have the left lifting property against every morphism in T, with the same for RLP of T. And so S is we can rephrase the quasi-category condition in terms of this language. So S is a quasi-category if and only if every inner Horn inclusion belongs to LLP of the map from S to the terminal object. And so, yeah, so this sort of language is already, I mean, I haven't really displayed that it's useful yet, but I've displayed that we can at least rephrase things in terms of it. And we have lifting properties in MATLib. They're defined in a pretty natural way. It's just, you have I has the left lifting property with respect to P if any commutative square that situates them on the left and right has a lift. And we also have RLP and LLP, which I think pushed to MATLib last month. And we define them in terms of morphism properties, which are in MATLib a nice way of talking about collections of morphisms. So it's sort of like a morphism property is a collection of morphisms according to some proposition that they satisfy. So given a morphism property T, LLP of T is all the morphisms which have, has lifting property with respect to any morphism in G. And RLP and LLP satisfy many nice properties, which I also pushed to MATLib last month. Here's some of them. Some of them I'll explain, some of them I won't. So if we have morphism property T, then LLP of T, it's stable under retracts, so is RLP. They're both stable under cobase and base change, respectively. They're both multiplicative, which means they contain identities and they're stable under composition. They're stable under coproducts and products, respectively. But two important properties here are stability under retracts and cobase change of LLP. So stability under cobase change means that if we have any push-out square and the morphism on the left is in T, then the morphism on the right is in T. And then sort of similarly for retracts, if the middle morphism is in T, then the outer morphism is in T. And so it's sort of easy to see why LLP behaves nice with cobase change and retracts, because these are basically, I mean, they're just commutative squares again. And so to solve a lifting problem, we can basically just glue squares together here. And LLP satisfies one more condition, which makes it weakly saturated. So it's stable under cobase change, it's stable under retracts, and it's stable under transfinite composition, which I haven't mentioned, but it's just sort of like a fancy type of iterated composition. And LLP is weakly saturated. So Joël Rioux showed that LLP is stable under transfinite composition in his small object argument repository. And then using that, I've defined sort of this class is weakly saturated, which I've been using in a lot of the arguments I've been going through. And one important thing about weakly saturated classes is the notion of the weakly saturated class generated by a collection of morphisms, which is just the smallest class containing those morphisms, which in Lean I've accomplished with just an inductive type, as you might expect. And so we need to make a few arguments using weakly saturated classes. In particular, if a class contains a collection of morphisms, then it must also contain the collection generated by those morphisms. And so we'll use that sort of argument with LLP being weakly saturated and containing inner Horn inclusions. So yeah, to that end, we need a few results. We need that the collection of monomorphisms is weakly saturated and generated by boundary inclusions. And again, if you don't know what a boundary is, it's not really important. It's just another sort of distinguished simplicial set. We need to talk about the class generated by inner Horn inclusions, which is called the inner anodyne morphisms. And then we need to show that the inner anodyne morphisms are also generated by a certain collection of what's called push-out products, which brings me to push-out products and the dual notion of pullback powers. So if we have two morphisms of simplicial sets, we can sort of whisker each of them, take the push-out, and then we get a sort of natural induced map from this push-out to the product, B times L. We call that induced map the push-out product of F and G. And in Lean, I've formalized it as such. So it's just a map from the push-out of A whiskered with G and F whiskered with K. I've been using notation, this little square, which I like. And I've been doing a lot of, so last month I did a lot of push-out product API regarding sort of how they behave well with retracts, cobase change, and transfinite composition. Of course, because I need to talk about sort of weak saturation and stuff. And this is used to show that the inner anodyne morphisms, the morphisms generated by inner Horn inclusions, are also generated by all push-out products of this form. So you take a boundary inclusion and push-out product with this special Horn inclusion. And the reason that these come up is because we have this dual notion called the pullback power or the pullback Hahn, where because of the adjunction between the function complex and tensoring, we get a connection between what's called the pullback power, which is induced by a similar diagram here, and the push-out product. So in fact, the following lifting problems here are equivalent. So if we have the push-out product of F and G, if that has the left lifting property with respect to H, then F has the left lifting property with respect to the pullback power of H and G. And so this is sort of how we can connect a lifting problem involving the function complex to a lifting problem involving a push-out product. And I've not fully formalized this adjunction. I would like to do it in full generality, but for the arguments I've been making, I only need really some special cases. So for example, when Y is the terminal object, sort of this second diagram, this pullback kind of disappears and just becomes the function complex of K and X. It's a lot simpler, but I would like to formalize this in full generality later. So to sort of summarize what we need for the argument, when we put together that LLP is weakly saturated with the adjunction of lifting problems, the fact that monomorphisms are generated by boundary inclusions, that inner Horn inclusions and these push-out products generate the same class, we're able to reduce the quasi-category lifting condition for the function complex to the quasi-category condition for S. So for example, part of the argument looks something like this, just for illustrative purposes. I didn't want to really go into the proof so much because I think this talk is already quite technical and has a lot of definitions, but S is a quasi-category if and only if LLP of the map from S to the terminal object contains all inner Horn inclusions. And since LLP is weakly saturated, that's if and only if it contains all of the push-out products, because they generate the same class. And then the adjunction of lifting problems lets us translate the quasi-category condition on S to a lifting problem which involves the function complex. And then a similar argument, sort of using monomorphisms and boundary inclusions, lets us get the quasi-category condition that we want on the function complex. So that's sort of a brief and imprecise sketch of the argument. And so what's missing in my formalization to make this argument work is just two points. Everything else is formalized. The full skeleton of the argument is formalized. There's just basically two stories, which is that the collection of monomorphisms is weakly saturated and generated by boundary inclusions. Weak saturation is not too difficult. I'm not really worried about that. I just haven't. All I need to show is stability under transfinite composition, and I just haven't gotten around to that. But generation by boundary inclusions is more technical, and especially showing that interanodyne morphisms are generated by all of these special push-out products. That's also very technical. And to prove both of those things, we need to sort of have some API for subcomplexes of simplicial sets. And so a subcomplex is a sub-presheaf, if that's helpful. Basically, we can sort of think of it as like a subset of our simplicial set. So we can think of it as like a simplicial subset. We can take unions and intersections in a natural way, just object-wise, and they in fact form a complete lattice, and we think of them as subsets. And so one important subset. So for an integer k, the k skeleton of a simplicial set is a distinguished subcomplex, which I didn't think it was very illuminating to define, so I'm just leaving it vague. But it's basically it's a nice like building block subcomplex. So in particular, the k skeleton is contained in the k+1 skeleton, and the union of all k skeletons gives us back our simplicial set. And the inclusion of the k skeleton into the k+1 skeleton fits into this push-out square, which kind of tells us that the k+1 skeleton is obtained from the k skeleton by attaching copies of the standard simplex. And so in that way, we get a really nice like building block. We can sort of build up our simplicial set using the so-called skeletal filtration. And so to apply this to monomorphisms, we want to show they're generated by boundary inclusions. So we can take monomorphism I from A to B. We can then view A as a subcomplex of B, and we can take this filtration where we embed A into A union, the skeleton, and then so on and so forth, and that lets us view I as a transfinite composition. So then it reduces to just showing that each intermediate inclusion is generated by boundary inclusions. And the push-out that we have from the last slide sort of gets us there. We can express each intermediate inclusion as a push-out of a coproduct of boundary inclusions. And then weak saturation stability tells us that, okay, monomorphisms come from boundary inclusions. So that's good. What's needed here is API to talk about the skeleton in a good way, and then sort of phrasing this push out in the right way as well. That's also something to be done. And then so the other missing ingredient is showing that interanodyne morphisms are generated by these special push-out products. That's also non-trivial. I mean, so Inner-anodyne morphisms are generated by inner Horn inclusions. So it suffices to show that inner Horn inclusions come from push-out products, and push-out products come from inner Horn inclusions. And one direction is pretty easy. To show every inner Horn inclusion comes from a push-out product, it's just a simple retract diagram, which I've already formalized. But going the other way, to show each push-out product comes from inner Horn inclusions is very technical. The idea is similar to what we did with monomorphisms. So we take the push-out product, we view our push-out as a subcomplex of the target product, and then we just adjoin subcomplexes into it in a particular order, such that each intermediate inclusion is generated by inner Horn inclusions. And I didn't really bother explaining how it's done because it's not something really easily absorbable by looking at. So I feel like it's not illuminating to include, but it's a similar idea. We build it up piece by piece. I don't think there's really any API that's really necessary for this. Like with monomorphisms, we need sort of skeleton, but here it's just a matter of just elbow grease, like really implementing these certain subcomplexes and showing that everything composes nicely. But yeah, after that, that's all that's left to do, is this really messy technical part. So yeah, to summarize, a proof that the function complex is a quasi-category when S is almost formalized. What's needed now is just I need to sort of work on degenerate and non-degenerate simplicities, which I didn't mention, but they're related to skeleton. I need to work a bit on sort of subcomplex API. And then, yeah, skeleton and the skeletal filtration, that'll be a big part of it. But other than that, it's almost done. So I'm pleased with myself. And that's it. Thank you.